discussing compositions and inverses today. So I'm going to start us off with compositions, which I don't think we've done before. So this is just another thing that you can do with functions. So besides using basic operations, another way you can combine two functions together is known as compositions. We may have talked about these in Honors Math 3. It may have depended on who your Honors Math 3 teacher was. Basically what happens in a composition is that you take two of them and one function becomes the input for the other function. So your notation is that you will have f of g of an input. The other notation is instead of using a bunch of parentheses, we use an open circle, which stands for of. All right, it's not a multiplication sign. It is of. Okay. Did you have a question, Miss Willis?
I don't think so yet.
Okay. I just thought I heard you make noise.
I was just agreeing with you.
Okay, thanks. All right, so let's do some examples. It says, given the following functions, find the requested compositions. All right, so in number 1, it says f and then a little open circle for of g of x. So what that means is that g of x is going to be the input for the function f. So we're going to take g of x and we are going to input it into where the x is for f of x. So we replace the x with all of this. So instead of x squared, I like to write a blank squared. And then inside the blank, we put x plus 1, which is the g of x function. So that would be your answer. You don't have to solve anything. We're not finding out what x is. If you want to simplify that, the only other thing you could do is actually square out x plus 1 squared, which remember is x plus 1 times x plus 1. So you get x squared plus 2x plus 1.
Oh, dang. I really thought I could just write x squared plus 1.
No. You got to remember it's x plus 1 times x plus 1.
Foil.
Yep. Foil that junk out, yo. All right. The other type of problem you can have is when they actually give you a real input for the x, an actual number. So when you do this problem, when it says g of f of -1, they're telling you to start in the parentheses. Always start in the parentheses. They're telling you do f of -1 and find out what that would be equivalent to. So I'm going to take that -1, make that the input for f. So I'm going to take -1 and square it.
What?
You get -1 squared and you get 1. Yes. So I'm going to replace that with a 1. And now I'm going to work on the rest of the problem, which says take g of that result. So I'm going to do g of 1. So I'm going to take that input and that input is going to go into g. So we're going to take 1 plus 1 and get
2.
2. Oops. All right. The last problem here says g of h of 0. So h of 0, we are going to put that as the input into h. So put that in for your inputs there. And -4 times 0, subtract 2 is going to give you a -2. Do the rest of the problem. G of -2 means you're going to take -2, put that as the input into the g function, and you simplify and get -1.
Whoop, whoop.
All right. So you will also be asked to find the domain of the composition. Usually that's pretty straightforward, but if you have a more complicated function, like one that has a square root, one that has a fraction, sometimes you have to think a little bit harder about the problem. So let's just go through these real quick. It says for part A, find the domain of f of x. If you need to, you can graph these in your calculator. So pause the video and graph them in the calculator if you want. But hopefully you know that x squared plus 1 is a parabola. So the domain goes from negative infinity to infinity. For g of x, is the parent function square root x. We gave you parent functions back in the first unit that we did, unit A. So you might want to go back and reference those. But again, you can graph that in a calculator to look at it. But the domain goes from 0 to infinity. All right, so if I ask you to find the composition f of g of x, again, that means we're going to take g of x, put that as the input in f, and then simplify. So that's going to look like square root of x squared plus 1. So the tricky part of this is when I simplify that, what happens to the square root and the squared?
They equal x. They're inverses of each other.
Yeah, they're inverses of each other and they cancel each other out. So if I simplify that, I just get x plus 1. So if I just look at that expression x plus 1, I think, oh, that's just a line. And a line has the domain all real numbers. So here's the tricky part. It says because the domain of g of x is restricted, this is what I mean by restricted, and only goes from 0 to infinity, it's not all real numbers, it's going to restrict your answer for the composition. So this part right here you need to look at when answering the question, what is the domain of f of g of x? So you want to look at your unsimplified answer to figure out what the domain of the composition is. So if I look at that square root of x, I need to think about, can I plug in any number I want to into the unsimplified answer? And the answer to that is no, I can't. I can only use numbers from 0 to infinity. So our answer to this is 0 to infinity.
Pro tip, if you type in the
Oh, yes.
simplified version into your calculator, it will only graph the part that exists to check.
Yeah, so it will graph this really weird line that just looks like this instead of graphing the whole line.
You have to type in the unsimplified, what she wrote in purple.
Yeah, so if you typed in y equals square root of x squared plus 1, your calculator knows, oh, I cannot use any negatives for the input because it knows it cannot take the square root of a negative. So it just graphs like half a line. It's pretty crazy. All right. Now this is something that I think we spent like maybe a warm up doing in Honors Math 3, and that was doing compositions of functions graphically. So all this is remembering that in the parentheses is your input, which is x. And we're going to read the results off the graph. So remembering the input is x, that means the output is going to be y. So starting with number 6, if it says g of 1, 1 is your x, so that means the result we're looking for is y. So g of 1, we're going to use the graph for g. So it's basically saying when x is 1, what is y? So that's going to be 1.
Like the point. Trying to find the point. They gave us half the point.
Yes, so they gave us the x coordinate for the point. We want to write down what the y coordinate is. So when we do compositions, it's going to be the same idea, except it's going to be basically a 2-step problem. So for number 7, when it says f of g of 0, you want to start always in the parentheses. So you're going to start at g of 0. It's like order of operations. Start inside the parentheses first. So we want to look at g of 0. And so when x is 0, what is y?
4.
4. So now we're going to do f of 4. So now you're going to go to the graph for f, and you're going to go to where x is 4. And when x is 4, you're out here. And then I notice, there is no graph. So what do I do?
If there's not a graph, I feel like it's impossible.
You're right, it is impossible. So I'm just going to say no solution, or you can say does not exist. Either of those things. So that one's kind of weird. All right.
I like weird.
You do like weird?
Love it.
Yes. All right, f of -2. So f of -2, again, you're going to start inside the parentheses. So f of -2, we go to where x is -2, and we look at what the y value is. And that's a 2. And now the problem says find g of 2. So you go to the graph for g and go to where x equals 2.
-2.
Looks like it's not exactly -2.
2.2.
Sure, -2.2. If you have to estimate, then estimate. So if you think it's at -2.3, that's fine. If you think it's at -2.1, that's fine. That one's just kind of an estimate. All right. I want you to answer these other ones on your own. All right. Decomposing functions. So decomposing is going to be the opposite of composing. So instead of putting functions together by putting the input in to the other function, I now want you to take the function back out. So this is going to be a situation where the functions have already been put together, and now I want you to figure out what the two functions were. So it's like a little puzzle. And so I've put a little hint on your paper here. It says you need to kind of think to yourself, which one of these was probably a parent function? And then that's probably your f of x. And then the other one, the other thing that you can kind of see there would have been the input. So what I mean by that is I see a square root in this problem. So when I see that square root, I kind of think, all right, there's a parent function that's just square root x. So if I think about this as being like square root x as the parent function, and then think about what the function actually says right now, the fact it says square root of x minus 1, that means that my input was changed to an x minus 1. So what we have is probably that one of my functions was square root x, and the other one was a new input of x minus 1.
Okay. So you can kind of check your answers too. Like I should be able to plug in g into my f function and get the OG problem.
Yes, the OG problem. Yes, so x minus 1 would be the input that you would put into the parent function root x to get the original up here.
Gotcha.
All right. Now, for some people, this is like totally obvious. Like, oh yeah, I totally see that. And other people, working backwards is a complete pain and will take some practice. And
I think a good hint is like, what was the apparent function? I think that's a pretty good hint.
I think so too, which is why we wrote it on our notes. I think everything that we do is a good idea, but other people might not agree with us. All right. So this second example, I see the fraction and I think, oh, we had a parent function that had a fraction. Okay, so that parent function was something over x.
It was
I noticed.
1.
It was one of
But
these.
this one is 2.
And that's okay. That just means it's that parent function too. So I'm going to leave that as a 2 over x, and then think about what would have been the input into this to change this to 2 over 3x plus 1.
Hmm.
So what would have been the input?
3x plus 1.
Oh my gosh, you're a genius. So again, this 3x plus 1 would have been put as the input right here to create this result.
Why couldn't I have just like put it as 1 over x, like, and then just made the other one like 2 over 3x plus 1? You know,
So your question was, why couldn't you have put
like the parent function 1 over
1
x,
over x and then put the other one as what?
2 over 3x plus 1. That would have been like, because you said parent.
So then I did say parent function. So if you had this, you want to check your answer and see if it works. So then you want to see, can I put this as the input into here and get the original? So you would have 1 over 2 over 3x plus 1.
Ew, no. Okay, okay.
Ew.
I got you. I got you.
So that doesn't work. Now, there are some problems that have multiple correct answers.
Yes.
But this that we just did in blue is not one of those correct answers. All right. And now I'm going to turn it over to Miss Willis.
So inverse functions. So when we're talking about inverses, it's you're given the relation of this ordered pair. If we look at this, the inverse would be BA. So what do we notice is happening there?
The X and Y are switched.
They're just flip-flopped, exactly. So we're going to recall the vertical line test can tell us if the relation is a function or not. I also call it like the pencil test. If you can take your pencil and move it across that graph and it only hits it once, then it passes. It's a function. And then we have the horizontal line test, which is kind of new. I don't teach Math 3, so I don't ever know what you guys have already learned.
We
But
did it.
that tells us that if the inverse is a function or not. So the first example says, here are some graphs. Is the relation a function, and does the inverse make a function? So here, if I do vertical line tests, does it ever hit it more than once?
No.
No, so this one is a function. Okay, we're just gonna, number 1 is fun, or part A is fun, and part B, to see if the inverse is also fun, we're going to do it horizontally. Will it ever hit it more than once if your lines are straight?
No.
No, it will not. So that means that the inverse is also fun. It's also a function. Okay, now looking at this next one, if I drew a line or took my pencil, it would hit it bam, bam. So no way. Not a function. It is not fun.
Not fun.
And then for the inverse, also not fun.
Not fun. But I'm having fun.
Yes, that's what I hope and dream for everybody. All right, so the next question says a function whose inverse is also a function, meaning it passes both tests, is called one-to-one. So which one of these is one-to-one because it passed both?
The first one.
Yes. So not only is it a function for regular, the inverse is a function, it is also one-to-one. Does everything have one-to-one? No, remember they both. 1, 2, 1 was this guy. This one, the second one, was nothing. Circles. Or an ellipse, I guess.
Yeah.
So, I guess I should have wrote this here. It was the first graph. All right, finding the inverse graphically. So we're going to graph the inverse of this function. So first thing we have to do is I make a table of values, because what the definition stated is that x's and y's are just flipped. So this is going to be my original function, which I'm just going to call f of x. Okay, so I have my first point. Let's not mess this up this time. We have 1, 1. My second point is 2 up to 3. Then this next point right here is 4,
3,
1,
3.
3, 1. There we go. I jinxed myself.
I'm paying closer attention today.
We have 4, 0. And then that very last point is 5, 3. So it says find their inverses in graphs. So to find the inverse, we're going to use the notation for inverse is f -1 x, that little inverse guy right there. And so the inverse table is just going to be them all flipped instead of 1, well, 1, 1 flipped is just 1, 1. So, but instead of 2, 3, it's going to be 3, 2. And instead of 3, 1, it's going to be 1, 3. And instead of 4, 0, it's going to be 0, 4. And then the last one, 3, 5. And then I'm going to graph this in pink. So we have 1, 1, still right there. 3 up 2 is right here. 1 up 3 is here. 0, 4. And then 3 up to 5. So this curve.
Oh, that's beautiful.
Yes. And so just based on the previous questions, could we say that this graph is 1 to 1?
No.
No. First off, I graphed the inverse, so we can even do the vertical line test to see. And had we done the horizontal line test, it would have failed. The first one was a function, but the inverse is not a function because it clearly does not pass.
Miss Willis, I think I remember from last year that if you have inverses, they should reflect over the line y equals x.
Okay. So,
right? So if you make that diagonal line, you should, whoa, that is not the line y equals x.
What y equals x? Well, I mean, I made it as
It should go through 1, 1, 2, 2, 3, 3, 4, 4.
Okay. If you try drawing a line on this.
I know. I can't do it either, but
dash, 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 dash.
that's better. Yeah.
Dash,
Because then the graphs will line up with each other if you fold it on that line.
That is a great thing to remember from Math 3, for sure.
Yeah.
All right. Finding an inverse function algebraically. They've given us these beautiful steps, and you can read them for your own. I'm going to jump right into it. It says find the equation, and then it tells me to give the domain. So when we think about, we'll talk about domain and range in a second. We're going to find the inverse first. So remember, f of x is just a fancy way of writing y. We know that that's y equals. When we were switching the points, we switched x and y. So when we're finding it algebraically, that's exactly what we're going to do. So instead of y equals, we're going to say x equals. And then both of the x's are going to become y's, like growth. So we got to get y by itself some way. And you're probably like, how, Miss Willis? Well, watch me.
How, Miss Willis?
Watch me math. I'm going to multiply to get that out of the denominator. So all I did was, again, multiply both sides by y plus 1. Now, you're probably like, could I just divide by x? Well, what is that going to do?
Nothing.
It's still not gonna, yeah. So let's think of a different plan. What else could I do to get rid of parentheses?
Distribute.
Yes. So I'm going to distribute that x, and I'm going to come over here, and I get xy plus x equals y. Now, so again, you're probably thinking, where do I go from here?
I think you just give up.
I wish that was that simple, but we don't do that. We don't give up in honors pre-calc. No, we figure it out. So I'm going to get my y's on both sides. So I'm going to put xy. I'm going to subtract the y over and see if this helps me with anything. And then I'm going to move that x over because it doesn't have a y. So I just kind of flip-flop them. And then I'm like, okay, well, I noticed something about the left-hand side. What do you notice? You notice anything about this left-hand side?
They both have a Y.
Yeah, so if we think about factoring, we can take out a GCF of y and get x minus 1.
Then we can divide.
Yes, there we go. And so I'm going to come over here and write my inverse notation because that's the way we want it. And I'm dividing, I have negative x on top, and I'm dividing by x minus 1, that whole parentheses. So now I have found the inverse of that original function. The second part says give the domain. So if we think about this, we need to give the domain of the inverse. Well, if we're switching f's or x's and y's, then we're going to be switching the domain and range of the original problem, usually, unless there's some problems, which we're going to talk about. But here, so if I have x plus 1 was my original function, if we were to graph that and look at our handy dandy calculator, we would see that the domain for this function was negative infinity to negative 1 and negative 1 to infinity. And the range for this guy was negative infinity to positive 1 and 1 to infinity. Again, looking at my graph, just saving us a little bit of time here. With the inverse, we just flip these. Now, could I have just looked at the original problem or the new problem? Sure, but we're going to see why in the next problem you can't do that. So I would always look at the not inverse domain and range. So the domain for this guy is now negative infinity to 1 union 1 to infinity. It's just the range of the function. Cool. All right, this doozy of a problem, you're probably like, why? It looks so easy. Okay, here we go. This is y equals the square root, so I'm going to say x equals the square root of y minus 2. So to get y by itself, what do you think I should do first?
Square.
Yes. So I get that y minus 2 equals x squared. And then when I move it over, I get that the inverse is x squared plus 2. So let me fix my notation here because we want the pre-calc fancy function notation so that we know that it's the inverse. Because if I just put y equals, how would we know? How would we know? So
I don't know.
inverse, oh, well, this is the inverse. Is the inverse a function? So we're going to talk about that. So clearly, this guy is a function. It's just a parabola. But if it were to ask us what is the domain of the inverse, so remember what I said. When we were to look at the original problem, we would see that this is a square root function. And a square root function looks like this. So the range of that was not it's not everything, right? So the range was restricted. The range for this guy would have been 0 to infinity. Okay. Now, if we look at the inverse, you would think it's a parabola, but remember, we're graphing the inverse of the original function. We don't have a full parabola in this problem. So we need to restrict it so that we only have the half that we want that is forming. So that's why we need to take the range of the OG function is my new domain because we only want the half. We only want half. So we would want just this guy right here. So is the inverse a function? Yes. It's just restricted. All right, last problem. Sometimes we have to prove. We always think, oh, I hate proving. Proving in pre-calc is a little bit different. You don't have to have all these rules and all this same side, all that stuff. So given two functions, f of x and g of x, we have to find the compositions of both. If these compositions are inverses, if these compositions, equal x, not x squared, not 2x, just x, then they are inverses. I have a strong feeling I am only going to be doing one of these guys. So we are going to do f of x equals 3x minus 4, and we're going to find, first we're going to find f of g of x and see what that equals. So that means I am taking g and I'm going to plug it into the f. So I'm going to write f with an open parentheses where I'm going to plug in my g function. So I'm going to take all of g and I'm going to plug it in. So when we are multiplying, we understand that this 3 is over 1. So I would have a 3 on the top and a 3 on the bottom. So
They cancel out.
Exactly. Yes.
No.
X plus 4 minus 4. And then if I keep simplifying, it equals
X.
which
Isn't
is
that
exactly
what it said?
what I thought. Yes. But
So,
the fun part is you got to do it the other way because we're proving it. So I have to prove g of f of x equals the same thing. And if it doesn't, then they're not inverses of each other. So now I am taking g's function, and where that x is, I'm going to plug in 3x minus 4. Okay, well, putting that in parentheses really didn't do anything. What can clean up on the top?
the 4s.
Yes, say goodbye, say goodbye. So we have 3x divided by 3, and that equals
X.
So yes, we have them both equal to x. Okay, therefore, they are inverses.
What's that symbol mean again?
Therefore, the little triangle.
Therefore.
Nicholas loves the symbols because she can't spell. Yeah, so I'm going to leave number 2 up to you guys, another on your own, and that is it for today's lesson. It has been quite the pleasure, friends.
So much fun.
That is